So today we start looking at the sensory system. So what we're going to do the visual system, somatosensory system, and auditory system. And these extend quite high up into the brain. So in primates, the visual system consists of almost 50% of the cortex. So it's a very large when you go from sort of low to high levels. So what we're going to do is start in each case at the receptors. And before we start, I just sort of introduce this idea of processing streams, and partly to sort of argue with it. So if you sort of really step back from all the different sensory systems and look at what are some of the sort of common threads that they have on how they actually process sensory information, one thing you'll find is it's very common for there to be a situation where you have some input coming in from the receptors. So here's the receptors, and that input from the receptors is then differentiated into a couple different streams that emphasize different aspects of the information. So they're physically separated into streams. And then those sort of go up to some processing stage. And often so for instance, in the retina, we'll talk about receptors that are more sensitive to rapid changes in the state of the input. And a receptor like that might be adapted to detect motion, because motion is sort of like, fast as opposed to something like shape. And so often the feeling is you've differentiated off something that sort of detects rapid changes, and so that's the motion pathway, like a motion pathway. And so the idea is that, maybe we could sort of trace that through up to higher levels. We can see like motion pathway at higher levels and then go off in another direction and maybe have a pathway for processing objects. So that way of thinking has a certain relevance to it, but when you actually look at the circuitry, what happens is once you get up into one of these places, everything sort of often gets mixed up quite a bit. But then when you look at the output of that stage, once again you have streams. So you differentiate you combine the information and then differentiate higher level specializations of the information. And so that's kind of the general. So rather than hoping against hope that you could trace a stream that went all the way through, in fact what you have is the creation of a higher level set of streams and then mixing in a creation of a higher level set of streams. And so that's really what we're going to talk about, the initial differentiation of the information starting from the receptors, and how that one stream of information from the receptors is turned into multiple streams. But don't get the idea that there's just one stream that goes all the way through. Unfortunately, it would be easier if it was that way, but it isn't that way. So what we're going to start with is the retina, and at the receptors in the retina. And so the retina, remember, comes from the optic cup, which was an outpocketing of the brain. So the brain actually sort of bulges out, the neural tube bulges out, and then the outer layer of that cup is the retina, and the back layer of the cup is the pigment epithelium. And so the pigment epithelium, we'll put it up here up at the top. So this is pigment, and if you look in a human, the pigment epithelium, human retina, looks like a black felt layer. It's designed so the light actually comes in through the retina, and the photoreceptors are touching the pigment epithelium. So it goes through the circuitry in the retina. The light goes through the circuitry, and then it hits the photoreceptors. And then any light that doesn't get absorbed by the photoreceptors gets absorbed by the pigment epithelium so that it doesn't reflect back. And that contrasts with the situation of something like a cat. You know, like a cat it's a nocturnal animal, and it has shiny eyes. You shine a light into a cat's eyes, you get a reflection off the cat's eyes. And the reason for that is that basically the light is going through, maybe hitting the photoreceptor and reflecting off the pigment. They have a reflective pigment epithelium, a reflective layer on it, and that reflects it back, and then it gives the cat a second chance to capture a photon. Why don't we do that? It seems like that would be a good thing. The reason we don't do that is because when it reflects off here, it scatters some, and so that causes blurrier vision. So cats are have much better vision at lower light, but it's a lot blurrier. They're like about 2200 by human standards, much more blurry than human vision. So the photoreceptors, they're called, you've probably heard of rods and cones. So the cone part, this is kind of the cone shape here, comes from these little folds of the membrane where the photopigments are sitting in that membrane. And there's probably 1,000 folds, but I've drawn, that's about 1,000. And so what happens, and so this is the nucleus of the photoreceptor. So interestingly, when you look at the photoreceptor, if this is 0, the photoreceptor is somewhat depolarized. It's usually about -30. And there's something called a dark current. And the dark current, so there's current continuously flowing through channels in order to depolarize the cell. And what happens is those channels are open, current is flowing in, and then current and then potassium is actually flowing out through the resting potential channels to try to get back to -70, but it never gets back to -70 because these other channels are permanently open. And there's a lot of biochemistry of how this works, how the photons come in, they hit the pigment. How does that eventually affect the protein that's holding the pigment? How does that cause some phosphorylation? How does that eventually lead to change in the membrane potential and essentially closing of the dark current channels to cause the cell to hyperpolarize? Because that's actually what happens when you turn on a light. Photoreceptors hyperpolarize. They don't spike. They just become sort of temporarily more polarized like that. And so that's in response to the light. So here's the light. So you turn on the light. So this is light. So they're all inhibitory in a way. So they just get more negative, but don't actually spike. And the reason they don't have to spike is because they're connecting right to another cell, which is sort of here. So here's an off bipolar. So this off bipolar cell makes a synapse like that. So there's little vesicles there. So that off bipolar also has just a simple hyperpolarizing response. So the off bipolar does the same thing. When you turn the light on, it actually just hyperpolarizes, just like the photoreceptor. So there's another, and this is the beginnings of the creation of these streams. There's another type of synapse here. It's a funny looking synapse for the on bipolar. And so what the on bipolar does is there's the dendrite sort of sticks up in there, and there's this little thing called a ribbon synapse, and it's a sign changing synapse. So when you look at the on bipolar, what happens is this guy actually depolarizes, just like you would expect a normal neuron to work. So that's the on bipolar. And what's happened is you've actually sort of taken one signal. So there's just one kind of a signal, which is a hyperpolarizing signal, and you've turned it into two different signals. So the on cell is more one that you would sort of think the way visual systems should work, which is that you turn the light on and it gets depolarized. The off one is actually the way that the photoreceptors work. And this one actually prefers to have the light off. And so it actually, when you turn the light on, in some sense it doesn't like it. It really likes the fact, it likes when you go from a situation of light on to light off. That's the most preferred situation. So one thing I didn't fill in about the photoreceptors. So for the photo, so these are receptors. So there's four types. So you basically have three cones, and the cone types are basically red, green versus blue. So the original distinction was red, green versus blue. So if you look at something like a squirrel has color vision, and it has one red, green cone and one blue cone. It's interesting to sort of look at the history of color vision. Birds and reptiles have very good color vision, turtles. And what happened in the origin of mammals is they kind of sort of destroyed their visual system and then kind of reconstructed it. And so the color system that used to be there in reptiles, involving colored oil droplets in the photoreceptors, is no longer there. And a separate system developed because mammals evolved originally nocturnally, and then as they came into the daytime, then some of them, like primates in particular, evolved color vision. But many mammals still don't have very good color vision. So if you look at a primate, they differentiated, they duplicated the gene for the red and the green cones, and then differentiated one of them so that they became sensitive to different wavelengths. And so it's kind of an asymmetrical system. You have sort of a red and a green system, which are very similar to each other, and then you have a separate blue system. And then separately you have the rods, and the rods are kind of more sensitive to sort of greenish color, and they work best at night. And so these guys are the bipolars. Bipolar cells. So you have photoreceptors, bipolars. It turns out there's actually another one here that I didn't show you called a rod bipolar. So we'll just draw that in, plus rod bipolar. And the rod bipolar actually rewires the retina. So what happens is, if you go in the dark for a while, what happens is the circuitry of your retina actually gets rewired so that the rods, which I haven't drawn here, this is a cone, the rods actually get wired through the rod bipolar to the ganglion cells, the same ganglion cells that are normally, they're down here, I haven't drawn them yet, same ganglion cells that are normally driven by the cones. And this takes a couple minutes for you to dark adapt, and you literally are just rewiring the circuitry of your retina so that the rods are hooked up to the ganglion cells through the rod bipolar. So I didn't draw that one, but it's there, plus rod bipolar. So then we go on to the ganglion cells. And so the ganglion cells are the first ones that actually spike. So here's an off ganglion cell, and here's an on ganglion cell. And I'm drawing them as circles, but they're, they have dendrites extending throughout the in thin layers throughout the retina. So this guy goes down and synapses here, and now and there's vesicles there. Some vesicles, and so that these guys spike. And so these guys, since the distances here that we're talking about are so small, the bipolars and the receptors don't need to spike. So these guys are the ganglion cells. And so what do these guys look like? So if we start off with the on ganglion cell, that's sort of a more understandable one. So if we turn the light on and off like that, what does the spike pattern of an on ganglion cell look like? Well, it might be spiking occasionally in the dark, but then when you actually turn on the light, you get a huge burst of spikes, and then it settles down, usually a little bit, and then when you turn it off, there'll be absolutely no spiking, and the cell might even be slightly inhibited, and then it'll go back to occasionally spiking. So that looks like what you expect a visual cell to do. You turn the light on, it fires. But it turns out the on ganglion cells are actually less common than the off ganglion cells. And so the off ganglion cells are very strange to most people. So here's a light. This is a light. So I didn't put the light in here. Let's put the light in here. Light. So the off ganglion cells are very strange. So what they do is they actually they're actually like the dark. So in the dark they'll just be like firing away, 200 hertz or something like. It's just like hard working. The retina. If you compare the retina to other parts of the brain, the retina is a hard-working part of the brain. It's really, the neurons fire a lot. It's extremely well supplied with oxygen, and it's one of the first things, if you start to get like diabetes or you start to get some problems with your circulatory system, it's one of the first things to go, because it uses up so much energy. A lot of other parts of the nervous system are kind of lazy by comparison, but the parts that are directly exposed to the input, they have to sort of do extremely high quality digitization, basically, of the data coming in, and so they're really sort of like just ultra adapted for not missing a beat, seeing everything that's going on out there. So these guys, bizarrely, are just firing in the dark, and then when you turn the light on, they say like, whoa, I don't like that at all. They might even be inhibited a little bit, fire a spike or two. And then when you turn the light off, that's when they completely go crazy. They really like that, and then they'll settle down to sort of a somewhat lower firing rate. So the cells, every time you turn the light on, they turn off. That's why they're called off cells. Off ganglion cells. And so these off ganglion cells, like I said, they're more common than the on ganglion cells in a human retina. So it's important, again, just to go back to the beginning. There's only one input. Well, there's red, green, and separately blue, but those all are inhibitory, and this on and off business has been created in the retina. And what creates it? Well, we should list one more cell type in here. So there's a cell type here that makes synapses called a horizontal cell. There's a couple types of those, and one type actually has two parts of it, so there's almost three types of these guys. But then there's another set of cells called an amacrine cell. Amacrine. Amacrine. And what it means is no axon. Now, unfortunately, some of these guys actually do have axons, but that's okay. And so these guys synapse with the on and the off cells, and these are the ones, the circuitry in the amacrine cell layer are the ones that actually are helping to create this on and off distinction. So so these guys are, amacrine cells. And there's a lot of those. There's maybe like 20, like 20 types of these. It's very differentiated. They all those 20 types tile the retina. So, ganglion cells, we have a whole bunch of different types of these. I just illustrated 2 there, but there's about somewhere on the order of 10. Bipolars, we've got 3 main ones of those. And, the photoreceptors, we've got, 4 different types. So lots of different cell types. And then these are the horizontal cells. We've got 3 types of those. That's these guys, and amacrines are these guys. So we got 2, but one of them, like I said, has 2 different parts of it, so it's almost like there's 3 of those. But we'll just say that there's 2 for now. Okay, so what does it actually look like if you look at a section? So if you look at a section, what you see like the pigment epithelium, and then you see like all the photoreceptors all lined up. And then you see a little bit off to the side all the cell bodies of the photoreceptors with little tiny wires attaching them. The photoreceptors are kind of like a little beefier. I'll show you some pictures later. So you see, so that's the photoreceptor layer. Then you see a big thick layer of synapses right in this region. And so you got synapses here. And then you have a layer that contains a thicker layer that contains bipolars and horizontal cells and amacrine cells. And then you see another big layer of synapses, and then you see the ganglion cell layer. So it doesn't really look like that when you. So you basically just see you just see 3 layers, something like that, of cells. And so this is basically. This is photoreceptors, this is horizontal bipolars, amacrine cells, and this is ganglion cells. And once again, just to reiterate, the light comes in here and then hits the photoreceptor that way. So this is the, inside of eyeball here, inside of eyeball, inside of eye. So if you look at insects, some insects have sort of done it what would seem to be the more sensible way, which is to put the photoreceptors first and have the light hit them. But this is the way we do it in mammals. And then what happens in the fovea is that the photoreceptors get sort of pushed off to the side. Sorry, the cell bodies get pushed off to the side, so that basically you get these little thin wires like this that go to the cell body of the photoreceptor like that. And here's the cell bodies of those guys all piled up. And so this is the fovea, in order to get all the circuitry out of the way so that you can have higher definition. That's right at the center of gaze, that primates have something like this. But something like a rat doesn't need a fovea. Okay, so so the next plan is to I'll leave the retin up on this side and talk about some of the additional subdivisions that happen in the retina. And so one of the main ones that appears is the distinction between transient and sustained cells. And this distinction is actually something that happens in all sensory systems. So it's not just in the visual system. And there's several generalizations that apply across those systems. And so if we look at sort of transient versus sustained, in each system they have slightly different terminology for describing the transient and sustained cells. And in the visual system, it's often for historical reasons, these are called X and Y cells. So X cells are sustained, Y cells are transient. But one of the things that characterizes transient cells everywhere in the brain or in the retina is that transient cells are bigger. So these sometimes are called, the magnocellular pathway, because they have much bigger cells. And so if you take the same type of cell, you can see this in the retina, and make it bigger, for instance, go out in the periphery of the retina where the dendritic fields get bigger, it becomes more transient. And so transient, or sort of rapidly adapting, that's another, we'll put that up there. Rapidly adapting, that's another synonym for transient, is associated with larger cells throughout the nervous system, same way in the auditory system, same way in the somatosensory system. So these guys are called, parvocellular, just meaning small-celled, and these are slowly adapting. So unfortunately in the retina, these guys are also called parasol cells, because they sort of look like, supposedly like an umbrella. I always make a joke that neuroanatomists, they spend so much time looking through the microscope that, if you looked through the microscope and saw this, you might not say umbrella. But and these guys are called midget ganglion cells because they're very small. And very unfortunately, sometimes this is called the M pathway, and then sometimes this is called the M pathway, and sometimes this is called the P pathway, and sometimes this is called the P pathway. It couldn't be worse. But those are all synonyms here. So for basically, transient, larger cells, more rapidly adapting, Y cells, and sustained, more slowly adapting, X cells, smaller cells. So this is in the retina. This is just in the retina, whereas magnocellular can refer to several different levels. These are retinal ganglion cells. And like I said, it turns out these are mainly the red and green business. And so there's another separate pathway, which is we could call this the coniocellular pathway, meaning small cell. But this is actually the blue pathway, and it's got actually sort of an on and off of its own, a separate on and off from the one I drew here. So I basically just drew the red-green pathway here, and these are actually quite small. So it branches into on and off, and these are small cells too. So sometimes these guys were called sluggish ganglion cells because their response wasn't as peppy as the X and Y cells. Or sometimes these sometimes partly overlap with the W pathway, but as opposed to XY. Okay, so those are the main pathways. And what is, if we just stick with this sort of X versus Y, what's actually going on here? So what's going on here is basically, so these guys, these guys basically sort of more or less give you the derivative of the signal. So this is more or less derivative, and this is more or less signal. And I say more or less because, in fact, both types have both kinds of things in them. It's just a matter of what they're emphasizing. So what do we mean by that? Well, if we look at a signal like this, so if that's the signal, f as a function of time, what does the derivative of that look like? The exact derivative of that looks like a spike right here, a positive spike, and then the derivative being the slope. And so then here the slope is 0, so it goes back to 0, and then now when you turn off you get a negative spike. So that's what the derivative, prime meaning a derivative, looks like. So are these cells exactly like a derivative? No. But you can sort of think of this in general as, these guys basically are looking more for the change in the signal. These guys are looking more for the actual amount of the signal. Because this, something that was a pure derivative wouldn't give you any signal as to how much was there. And we'll see that no cells are pure derivative or pure signal. So what do they actually look like? So let's just so we'll start off by just looking at the on and off cells in their transient and sustained form. So now we've differentiated the pathways into at least 4 separate pathways. So we start off with one kind of a signal here, but now we end up with 4 copies of that signal. And so last year I managed to shrink these graphs down way too small, so I'll erase this and make a nice large graph so we can see what's going on. And so what we're looking at now is the X on, meaning sort of sustained on, Y on. So we'll start with X on. So here's X on. So that's sustained on. So that's the one that sort of behaves most like you would think a self-respecting visual neuron should do. So here's the light. Here's the light. And so what I was doing here, these are actual spikes. These are actual spikes. But a lot of times when, in order to sort of quantify this, we often change over to, firing rate. And so I'm going to draw firing rate. So you could turn this graph into a firing rate graph. It would be like, a low firing rate here, and then a high firing rate here, and then a less high firing rate there. So that's what I'm drawing over here is the firing rate. So this way is spiking rate or firing rate. Spikes per second, spikes per second. So if you look at what's going on here, what you see is there's a finite background firing rate. It's not 0. It's not 0. So I'll draw the thing in red. Okay, so it's not 0. And then when the light turns on, there's usually a little bit of a delay before the response. And then there's a response that goes up, and then there's actually a transient response, like you would have in a transient cell. But then the firing rate drops off a little bit, usually sort of habituates a tiny bit. And then when you turn the light off, there's a little bit of a delay, and then usually the cell drops down below the background firing rate, and then after a while it comes back up to the background firing rate. And so what are the features here? So there's several features here. So one of the features is, what is the delay? And then another feature is, what is the sustained response? And then another feature is, how big is the transient response versus the sustained one? So all those features can sort of be varied independently. And so if we look down at so that was a sustained version of an on cell. So if we look at that's X on, so here's X on. So now let's look at Y on. So the Y on cell is a transient version of that cell. And what does that look like? So that will basically, let's draw these lines all the way through. So here's the light coming on again, going off. So what happens to the transient version of the cell, not surprisingly, its background firing rate is actually tends to be lower. That might be a fourth, you could argue that's a fourth feature of it. So the background firing rate is a little lower. When the cell turns on, the response time is better, so it comes on quicker, and then the transient response is much bigger than the sustained response. When you turn the light off, it goes off again and then back up to its. So that one, so if we look at this one, you can see that this time is smaller. You know, this thing is bigger, and this sustained response is less. But all of them are there. So, you know, so basically an X-on cell just has a reduced transient. It has a bigger sustained part. The Y-on has a bigger transient and a smaller sustained part, but they both have transient and sustained parts. Okay, so that's our Y-on cell. And then the ones that are less familiar are the other ones, which I almost always ask the question about. They're actually more common. So like an X-off cell. So what does an X-off cell looks like? So this is light. So an X-off cell has a strangely different response. Oops. And it has, it basically has a, response to turning the light off. So it's not going to like the light when the light is on to start with, because here's the light. So it won't like it when the light is on, but it will like it. It'll have quite a high background firing rate to the light being off. And then when the light turns on, it really doesn't like that. But it takes a little while, it's got a little bit of a delay. And then what it'll do is it will come back to a small firing rate. And then when you turn the light off, that's where it really likes it. So when you turn the light off, there'll be like a nice big spike up to sort of like a background firing rate. So that's a classic X-off cell. So the light's off and it's just madly firing away. You turn the light on, and it gets inhibited and fires much less. You turn the light off. That's the best possible thing, is going from light to no light. And the Y cells are just sort of like you would imagine. So they have a slightly elevated firing rate when the light is off, and then when you turn the light on, they really don't like that, and they go back down to an even lower firing rate. And then when you turn the light off, they really like that, and they have a nice big spike of response, and then they'll go back to sort of a low firing rate. So again, remember what we've done. We've essentially just created four separate, so this is Y off. So we've created four separate responses from just this initial one response. I didn't talk about the red-green business here, but the red-green business is in there. So what is the red-green business? Well, we've got sort of a lot of different combinations, additional combinations. So we've got red on center and green on center. So one way you could think of this, so you can think of it, we start with, so we initially divide into on and off, but then we've got all these additional divisions. So you've got red and green. red and green. But then you've also got these Y cells, which turn out not to be sensitive to color. So these guys are sort of luminance only, luminance. So you have red, green, and luminance. So what do these Y cells do? So these guys are going to be, red or green. But these guys are going to be luminance. So what they do is they destroy the signal from the red and the green. So they just respond to the brightness, and they don't care whether it was red or green as long as it was a bright red and a bright green. Those would be just as good. So they're actually destroying some of the information. So this is another theme that you see. You often see you create streams, but you also throw away some information in a particular stream. So in this stream, we're sort of just concentrating on the luminance of the signal, and we've kind of thrown away the information about the color of the signal, whereas these red and green pathway keeps track of that. But then we have another separate pathway of on and off that has blue in it. So this is the blue pathway, or the conio pathway. And then we've got other types. So these are what I'm describing are all the different ganglion cell types that have been created. So we'll put this, we'll make this go down to our ganglion cell. So we start off. So we have on and off, red, green. So on red, green luminance, off red, green luminance, blue, on and off. But it turns out there's other ones. There's some direction selective ones. Those are separate ones. They go to a different part of the brain, direction selective, in the retina. And then in addition, there's some that there's something called a thorn cell, which goes to the superior colliculus. So there's a whole pile of them. So how many did I draw? I went 1, 2, 3, 4, 5, 6, 7, 8, 9, at least 10. So we've essentially taken that information, this one source of information, that's not counting the rods, and billowed it out to 10 different subtypes. Okay, so let's erase this for now and talk about another type that is actually created in the it's created in the geniculate of a cat. It turns out it's not created in the geniculate of a primate, but we'll come back to that later. Next time when we talk about a little higher in the system. And this, I already sort of introduced this idea of direction selectivity. So direction selectivity just meaning, is something going this way or that way, or, up or down. So one very simple way to make a direction selective detector is called, sometimes in the visual literature, is called a Reichardt detector. And so what does this look like? Well, if we've got a detector, I'll draw it in the standard way. If we've got a detector here, and we have a little delay mechanism here, and then we have some way of adding that together with an undelayed version of the signal, we can make a direction detector. Now, this addition has to have some kind of nonlinear summation in it. I'll explain why that is. So if you take an object, so if these are two detectors, so there are two detectors that are separated by some space, and one of them is delayed. So if you take an object and move an object this direction, versus moving an object in this direction. So here we'll just call that 1 and this 2. So what does the response from this detector look like? Well, let's do it the other way around. So let's do it first. Try the one where it's going the wrong way for the detector. So what will happen is there'll be a burst from this object stimulating this receptor. So there'll be a burst like that. And then a little bit later, there'll be another burst when it stimulates this detector. That burst would have been there, but it's delayed. So it actually appears here. And so you get a response. But the idea is if you put it through something that has some kind of a threshold, then it didn't reach threshold, and so there's no response. And it's not that hard to make a threshold. A spike is a threshold. It has a certain threshold to activation. And so if you lightly stimulate the cell with a postsynaptic potential, but not enough, you won't get anything. And then if you go above the threshold, suddenly you'll get a response. So that's this case. And then what happens in this case is the good case. So we stimulate this guy, and so again we get a response. We get a response. But the response would have been there, but the response is instead delayed because of this delay right here. And then that delay just happens to be exactly right so that when this guy responds without a delay, it gets added on top. And so then in that case, so here's the same threshold and you'll be above the threshold. So this is a basic mechanism, and it turns out there are cells in the cat geniculate that implement this, and they essentially divide these pathways into the 4 that I originally had here, which was X on, Y on, X off, Y off. They divide those 4 pathways into 2 each. So you end up with 8 possibilities, and the possibilities are called lagged versus non-lagged. And so there's all the possible combinations. There's X off lagged, X off non-lagged. And what is the lagged? Well, it's basically this pathway. So what do these cells look like? So these are cells in the geniculate. So this is in nota bene cat DLGN. So what these cells look like is if you turn. So if we take one, like what did I draw last time? So we drew Y on non-lagged. And then here's Y on lagged. So what happens is for the Y on non-lagged, low firing rate, and when the cell comes on, it looks just like the one I drew originally. So here's the light. When the cell goes off, it comes back. And as you might expect, the lagged just have a lag. And so here's the same thing, light on and off for a Y on lagged cell. And so what that does is it's going on, and then when the light comes on, it sort of gets slammed to the floor. And then after a delay, there's a nice big spike like that. And then when the light goes off, sometimes there's often another little spike. We'll just ignore that for the time being. But the big difference here is in addition to all those other things changing, the lag changes. And so this, you could basically look at this as, so here's the Y. Circle these so we can see them. But there's all the other combinations. So there's X off lagged and X off non-lagged. So you've actually turned these 4 pathways that I originally had here into 8 pathways. And how does this work? How do we think this works? In this case, you've got the input coming in, and what happens is it hits an excitatory cell, and that cell goes forward. But there's a very powerful excitation of an inhibitory cell which has a very rapid response. And this guy goes and does a temporary but very rapid inhibition of this guy. So that's actually how the delay is actually implemented by some very fast feed-forward inhibition. So this is fast feed-forward inhibition. And so that's doing this part right here. It's kind of slams off the cell for a while, and then, but it's very transient. It releases, and then the cell can sort of spike. And so this gives you some idea how cells are kind of engineering these processing streams. So they're essentially taking one stream of information and doing little engineering tricks with neurons in order to actually generate all these different response properties. And these cells, the lagged and non-lagged, are not themselves direction selective, but if you could basically use the on-lagged as the delay part and the on non-lagged as the non-delayed part, and all you have to do is slightly attach lagged and non-lagged from different parts of the retina, because you need a difference in where the detectors are in order to make this all work. So that's it for the retinal streams. So just to review, we got the retina, you got some photoreceptors back here, you got the bipolars that attach up to the ganglion cells. There's a bunch of circuitry created by horizontal cells that deals with this photoreceptor bipolar synapse layer, and then amacrine cells, a whole bunch of those guys that deal with the sort of bipolar ganglion cell connection. And the amacrine cell circuitry are the main ones that create all these different substreams of on and off, transient and transient versus sustained red and green, transient versus sustained red and green for off, and then the blue pathway, which has an on and off, and direction selective in the retina. So it's already direction selective in the retina. This is just like one stage on the way to making direction selectivity in the cortex. So there's already direction selective, and then some specialized ones that also go to the superior colliculus. So lots of streams. So we're creating all these different streams from the original source of information, with the purpose eventually of combining them again. So I think I'll stop there, and we'll ask for some questions.